And the first talk here will be presented by Enes, who is the lead data scientist at Noom.inc. In general, he is experienced in deep learning, NLP, computer vision, and his talk is entitled Predicting User Disengagement from the Events Data. So he will show how to use transformer models on heterogeneous events data to get predictions of user disengagement, and also embeddings for categorical data that can then be used on the other downstream tasks. So without further ado, I do hope you enjoyed the talk. I present to you, Enes.
Thank you all. So I'm Enes Deumic, lead data scientist at Noom, and I'm going to present predicting user disengagement from the events data. But first, let me tell you a few sentences about Noom. So Noom is a behavioral change company, and our mission is to help people everywhere lead healthier lives through behavioral change. Our main product is Noom Wait. It's an app where you can log meals, talk to coaches, etc. And the main goal here is for us to help you lose weight. First, I'll tell a couple of things that are in common with all mobile apps. Some business questions that you can try to answer with machine learning. And that's, for example, if you have a website, which visit is most likely to turn into a sign-up? Which sign-up is most likely to become a subscriber? How to keep users engaged? How to do meaningful interventions? How to maximize user satisfaction? Or how likely will the user renew subscription? Or if they quit, how likely are they to come back? In other words, we're trying to assess the lifetime value of a user. What's on our disposal? What data is on our disposal? Usually we have some demographic information and we have some user-generated events. In Noom case, we have actions like meal logs, weigh-ins, exercises, talking to coach, reading the content. All of this is the for purpose of changing your behavior to lose weight. The starting point in a user journey is when they're registering to Noom. So they go through the buy flow where we ask a bunch of questions, which are used in twofold. So one is to adjust the program to you. So for example, it's not the same to lose 50 kilograms versus 5 kilograms. Or it's not the same maybe for someone who's 60 years old versus someone who's 20 years old. Another useful thing for us is that we have some prior knowledge about the users in terms of predicting their lifetime value. So the goal here is to detect the early user disengagement. So once they start, using that app, try to act before it's too late. Once user is disengaged, it's much harder to get them back versus at the stage where they're just maybe thinking about it. And especially where you're trying to change user behavior, this is very important because, in other words, you're trying to make it a habit. And habit, every additional day that user survives increases the chances of them acquiring the required habit. Now you can use, for example, aggregated features like number of foods log, number of coach messages in last day, in last 2 days, last 3 days, all of that. That's okay, but it's not always good enough. And we have better data. One is, for example, user-coach conversations. So a coach message can be, a user message can be, I'm not satisfied with the coach. I would like another coach, or are you a robot or something like that? Or it can be, I'm really satisfied with Noom program. I have made immense progress and so on. They both count the same, but actually the meaning is completely different in terms of user disengagement. So we here will try to use the detailed data instead of aggregated data. Another very important thing is the logging dynamic. What does that mean? Well, that means that let's say that I'm logging meals that I'm eating, and then after that, immediately I log a meal. And I do that for a couple of days. I'm all pumped up because of the new app. But then I start, drifting. I start logging the foods later and later, and maybe sometimes even another day. And that change in micro behavior can be a very good signal for disengagement. So in order for us to do this, we've developed something called the user feed model. User takes raw temporal user information, transforms it, and produces two important outputs. One is predictions for the questions that we might ask. The other one is numerical representations. Now, let me give you a couple of examples of the questions. I will not read every one here. So, for example, what's the probability that in the next 7 days, a user will have a streak of 3 consecutive days without food logging? So some sort of disengagement. What's the probability of user renewing their subscription? Or what is the expected weight loss after 30 days? What's the sentiment about the messages, or which foods can we recommend to them? As for numerical representations, you can have rich numerical representation. So we have a lot of data about each user at each time step. And what we can do, we would like to have one fixed vector that represents this user, right? So in our case, it's 768 dimensional vector. And you can use then these vectors for predicting stuff, for clustering, for segmentation. Maybe you can, depending on these user vectors, on clusters, you can maybe give different experiences, try different stuff, and so on. Coach vectors, we have around 2,000 coaches. Maybe you can give certain users certain coaches. We can see which coaching style exists. We can see which coaches need maybe help or changing their the way how they teach, and so on. Food vectors, it's something we have rich databases of foods, and maybe we'd want to recommend foods, stuff like that. And then any other categorical feature like acquisition channels, is the user came from Facebook, Google, Instagram, and so on, and then to make, for example, better attribution models and all that. In general, vector representations are reusable for any downstream task. Now, what about the metric? Now, you have to think here in terms of what problems are we solving. If you look at this line, you see that at T0, user starts their journey. That's maybe a biflow. And at TQ, on the end, that's when the user quit. Let's say that user bought a 4-month subscription plan. And so TQ would be 4 months, T0 would be 0. Now, most of if you look at time periods, most of this line is filled either by engaged period or by disengaged period, which means that if you're engaged, you're very likely to be engaged tomorrow. Or if you're disengaged, you're very likely to be disengaged tomorrow. So a metric like, will a user be engaged tomorrow is it's pretty trivial to just predict what's today, right? So what we want to do is, if you see the TC and TD, that's the transition. So from the state of being engaged to state being disengaged, that's the transition period. And you need something that will first that we will look at this period more closely, and the second one, to have a metric which will take this into account. And this is done by disengagement streak metric at M and M days, which means that, for example, a streak of size M will start in the next M days. One example would be 3 at 7 would mean that within next 7 days, we expect a stream of size 3 to start, streak of size 3 to start, meaning that 3 consecutive or more days, user will stop logging, for example, food or content or whatever. Now, AUC, of course, for any classification, binary classification tasks can be used. It's good for classification, but it's not good for expectation. What I mean by that, often we need to do some action. For example, do we offer a discount or something? Since it's a ranking metric, to AUC, it doesn't matter if the distribution is between 0.4 and 0.6. If the ordering is the same, compared to distribution that starts from 0.1 to 0.9. And in scenarios where we want to, for example, offer discount or something, we'd rather our models to be, sure than not, regardless of the rankings. Results. So another thing that you can do, you try to, when you're training the model, you're trying to resample from the period from TC to TD as much as possible. Of course, we don't know which are these periods, but we can have some heuristics to find to be more likely, because periods from T0 to TC or TD to TQ are monotone. Model doesn't learn anything. But in the end, you will have to rescale your probabilities, normalize your probabilities, because if you tinkered with the training data, that will influence the probabilities. And also, you need to, whatever your baseline is, and you always have to have a baseline, we know that, it also needs to be with the same sampling technique. So what are we doing? We are using transformer models. Now, most of you probably already know that most of the papers end up being either from NLP or lately in computer vision. But actually, you can use transformer models for anything. So in this example, we are looking at the translation from English to German. But we also know that we can use only encoder, for example, in BERT model, or only decoder in, for example, GTP models. So for our case, we can use both. So, for example, we can use encoder model if we just want to predict disengagement, or we can use decoder model if we want to predict what's the next event. Now, we haven't played that much with decoders. There are some issues like the ordering of these events is not always, it's not important always. And it seems more straightforward just to use encoder and I'll show this in the architecture. That being said, one important thing, just if you know BERT model, you know that the first embedding. So here we have word embeddings, and they got transformed multiple times for the encoders, and by self-attention mechanism, they get mixed. They are using classification embedding as a special embedding from which they are doing classification. So let's say that this X1 is a classification embedding. It goes through the network, and it gets mixed with other embeddings from other words. But the classification is only done from the classification. This is the same thing we're doing. So we have a classification event, and the rest of are the events that we are that are happening. So here's a sample data set. You see that there are timestamps. You have event types. You have particular values, for example, for weighing, for meal, which type of meal was logged, which foods were logged in that particular meal, what was the coach message, title of the content. And then how does the model look like? Well, the model looks like, let me just first say about the input data. As you know, in transformer models, you have to have positional embeddings. For us, positional embeddings are the days of the program, so that they represent that. And they're summed with the DTs, delta T's, between the events. Okay, so we turn DTs into categorical variables, and then we use these embeddings as an input and this is basically a positional embedding. And then we transform all of our features to 768 dimensional input. So for events, if you have some event way for, let's say, food logging, you can have a breakfast. It would be represented by 768 dimensional vector. So therefore, combined models here actually. So one is in event transformer, one is food transformer, one is conversational transformer, and one is feed-forward neural network. Feed-forward neural networks we use for as an encoder to take all the features, for example, for buy flow, and turn them into 768 dimensional vector. The other three transformers take these 768 embeddings. And so the event transformer is just the event type and DTs, so distances between these events. A food transformer are food logs, so the food embeddings come into. So each meal consists of a couple of foods, and then the meal embedding is a sum of these embeddings, and this is the input to. And the conversation, of course, user and coach messages are encoded by some algorithm like BERT or something. We also try to do as much as possible self-supervised tasks, because we have a huge data set and we don't have that many labels, and we want good representations for all. So one of these self-supervised tasks is if you have a meal of 5, let's say you have a meal, coffee, eggs and bacon. We mask one of the foods randomly in that meal, for example, bacon. So you know that if there was eggs and coffee, that was probably breakfast, and we all really know and there's the very likely food is, for example, bacon and not broccoli or something like that, right? Or banana or whatever. So this is the way how we can, for each food log, we're also trying to predict which one is missing. Or we also try to predict is the message from the user or a coach, or if you have a sequence of 10, let's say, messages, user is a conversation, we randomly split this, for example, at position 7, and then we either continue conversation as it should, or we take a random sample from some other conversation and stitch it there, and then we try to predict if this is a continuation or is it a random. So this gives us better conversation representations, which can then be used by other tasks. So the question is probably, why 4 models? Well, it can be one model, don't worry. But we've built 4 because we have different teams like food, conversation, user coach conversations and all of that. And we can just give them these models, and they can, fine tune instead of training the whole thing. So let me just show you the architecture. So this is not a very nice picture of transformer, but basically this is what you've got. So demographic data goes through the feed-forward neural network. This then gets encoded at position 0. Then we have a event classification embedding, just like in BERT, and then we have the events. Okay, so all of this goes through the transformer, and we're making predictions from the classification embedding. Now, times 3 means that we, in parallel, have 3 transformers, and they share weights on positional embeddings and also on the classification embedding, right? They just transform the classification embedding in a different way. So yeah, here are some of the results. So a streak 3 at 7, meaning that a streak of 3 consecutive or more days of disengagement in the next 7 days. For example, for the user feed model, log loss is 0.41 and AUC is 0.94. While for the aggregated model, we have 0.47 and 0.85, which is significant improvement. The same thing here, a little bit lower score because it's harder to predict 7-day streak. Then we have top 3 for food classification. It's around 60% out of 85,000 classes that we use, 85,000 different foods. Now this seems, really good, and it is, but actually, this food logging distribution is very skewed, which means, if you always predict banana, for example, which is logged very frequently, you will already have a model that's 1% accurate. Predicting user coach message, that's probably around 99% or so. So here are some of the embeddings that you get. So food embeddings, the first row is the food embedding for example, white rice, rose wine, fresh strawberry, and here's the list of the most similar ones based on these embeddings. And you can see, for example, that you have a skim milk, then you have a low-fat milk, 2% reduced fat milk, all about, lower fat milk. Then you have a bacon, then you have all kinds of bacons you have wine, all kind of wines, rice, all kind of rices, then vegetables, very similar, very good letters. So yeah, that's it. Hopefully I'm done on time. So if you have any questions, please do.
Yeah, thank you for the talk and your insights into the topic. The first question is, you talked a bit about the challenges with repetition, but could you also mention some of the other challenges that you found whilst working on the model and on the results from it?
Yeah, the challenges was it's very hard to. I mean, this is enormous amounts of data from different sources, and thinking of good ways how to store all of this data and then fast reading this data. And while you're experiencing, you don't know what will work. So you have to have a flexible data structures and all of that so that you can easily add. For example, if you have TF records, you can't add new stuff, although it would be very fast to read and all of that. So we used AGF5 files where we could you had the canonical file with all the data, and then you would fastly create these data sets. And you can sample by keys, by user IDs in different ways and all of that, which would make training a little bit slower, but it would make you more flexible. Another challenge would be also having these, finding the good points where user is on this either in engaged and versus disengaged state, because some users are subscribed for example, for the last 3 years, and they don't do anything. And you would have a list, an event stream of days, which is thousands long, and wherever you pick, it's trivial to predict that this user is disengaged. So finding these sweet spots, so that these were the difficulties.
And speaking of users in general, let's say throughout this research, did you manage to find some commonalities in across time that you made, for instance, finding the disengagement point easier to do as you went along? And could you elaborate a bit what those commonalities were?
Yeah, so one trivial thing is that as more data you have, as user is engaging more, the model is more certain about what's going to happen. There are interesting points in time, for example, when the subscription period has to renew or something like that, where these, again, predictions become more unstable. Also, there's, if a user is engaged for a very long time, you can basically see that some users are, they have the habit. It's easier for them to predict stuff for them. That being said, right now we haven't explored 1% of the consequences of the model. So there's a huge space of opportunity to explore. One example would be maybe that's interesting is that, for example, app opens is a much lower signal than any particular engagement. So you have users who are actually opening the apps but not engaging in any meaningful way. And this is maybe an opportunity to see, okay, when are the scores pretty low and user is opening an app, then you can serve something to them to maybe re-engage them at that point, right?
And you might get this question a lot, but with the pandemic and how it changed how users can use their devices, all of them in the ecosystem, their own, and with them staying at home, or what was the firstly, how did you observe some changes in pattern? What were they? And secondly, how do you think going forward will this be more challenging, because pre and post pandemic data will differ vastly in actually helping predict future engagement?
Yeah, that's a good question. So one interesting thing is that engagement on its own is probably less influenced. It's more stuff like will you resubscribe? Will you cancel your subscription? Stuff like that is maybe more sensitive to economic outcomes. But the patterns in behavior are less. That being said, we are planning on using the vectors. You have this big model that's trained over long periods of time and all of that, and you end up with a user vector. But you can then use that user vector as an input to another model, which is much more sensitive to data, maybe to some tree model that's trained on the last month of data. So you can still have all the benefits of the user feed model, which is a strong model that extracts real deep signal, and apply it with new model on new data with new trends. So that's it's basically what it's doing then is correcting the probabilities, right?
Brilliant. That's it for the questions. Thank you once again for your insights. A rather interesting topic in general. So I hope you enjoyed the presentation. I hope you enjoyed the experience. And on behalf of the conference, I would just like to thank you for giving this talk.
Thank you for everyone who has been listening. I don't see how many or any are listening, so I'm glad to be here. Thank you very much.
Thank
Bye,
you.
Gnim.